Thanks very much, and thanks, Nick. It's really good to join you here today. I won't be dwelling on any detail related to Carmont. I don't think it's really appropriate for me to do that. But what I really want to do is guide you through some of the changes that have been brought about by Carmont and other previous incidents in respect to earthworks management. As mentioned, I worked on Northwest region as an asset engineer for quite a long time. And it was always enjoyable finding images from history of assets that you know and love, including Harbury cutting, Dove Holes cutting in the Peak District. One of the cuttings on the was the Grand Central line through the chalk, showing the steepness of the slopes. This is a generic image. I've no idea where it's from, but just gives you an indication of the way that earthworks were built. And I think it does us a lot of good to remember how the earthworks were built, because it feels quite chaotic, particularly to us who are engineers and have worked in civil engineering with modern standards and modern design approaches. I want to focus on change because there's a lot of it about. There always has been in the railway industry. Organisational change can occur anywhere. Any organisation goes through it, changes in personnel, management structure, new technologies. But we're subject to changes in legislation, political change because of our funding streams, and that affects the structure and the economy and the strategy of the business. We also see changes due to climate change, environmental awareness and that kind of thing, which have a really strong impact on the way that we manage stuff. And yes, we also get exceptional changes as a consequence of incidents such as Carmont. Really, one of the key moments for us was the Aysgill derailment in 1995 on the Settle and Carlisle, where very sadly the conductor of the train was killed, struck by another train. That really marked the start of Railtrack recognising that they needed to get geotechnical engineers into the business to start looking at and categorising the earthworks. And it led to the first earthworks asset inventory capture in 1997. Forza-Kruchen, a very dramatic derailment there with a boulder falling out of a soil slope, derailing a two-car DMU, really highlighted the risks associated with third-party land. Watford, of course, which could have been an awful lot worse than it was, with a passenger train travelling at 60 miles an hour, decelerating towards the tunnel portal of Watford and encountering chalk, which was washed down by an immense amount of surface water in a storm event, and led us to really focus more closely on groundwater, in particular drainage around tunnel portals. And Carmont, of course. And in addition to the RAID report, which Nick so kindly shared some of their findings with us, there was a Network Rail Level 3 investigation report, but the geotechnical team and civil engineering also commissioned a report by Lord Robert Mayor to have a look at our management of earthwork assets. Really, a lot of stuff came out of that. We were commended for our management structure for assets in the earthworks, but they did find one or two recommendations to make, 53 in total, across a whole wide range of things, from technology, interface with other disciplines, our diagnostic tools, examination, evaluation, the amount of data we captured, and so on and so forth. And really what we're doing now, and what is marking the change in the geotechnical industry, certainly, or the geotechnical business in Network Rail, is working through those and seeing where we can make improvements and how we can best capture the recommendations. We've also, of course, had a load of routine railway churn. I think I've been through about 5 reorganisations, had many, many titles whilst doing exactly the same job. But we've seen changes from this current structure with regions overlying 14 routes, change in leadership, increased devolution, focus on the customer, which was the point of PPF. And of course, also more recently, big political changes as funding is withdrawn from HS2 Phase 2. Potential for change in the future determination for how much money we have to spend. We're doing quite well in CP7, as to be said, but that could all change. And of course, the looming GBR, which may be BR if it's a Labour government, perhaps. But in all of those things and through all of that change, we have to ensure that the assets are managed, suitably equipped to adjust and adapt and develop so we can manage the portfolio through change. So it's really important that we have systems, processes, knowledge and learning in place to achieve that. Just a quick reminder of what our operating license says. It says that we need to maintain the risks of the operational railway, including personnel and members of the public, as low as is reasonably practicable. And what we do within the engineering professions is we look at what we call a bow tie diagram, in which we consider all of the controls, measures, standards that are put in place to prevent an incident from happening, consider the key incident that could occur due to earthworks in this particular case, and then we look at all the measures that can be put in place to try to manage the outcome of an incident if it happens and to minimize the damage that's done in the process. Our two top events in the orange circles there are a cutting failure leading to loss of capability gauge. That means stuff in the path of a train, and usually that's come from above. Difficult to understand how. Anyway, or for embankments, embankment failure leading to loss of track support and loss of track geometry, commonly recognized as loss of top, loss of track alignment, leading to twist faults, leading to derailment risk, and so on. Robert Mayer very kindly mentioned that we had a good, robust system in place. And what we do is we examine the earthworks, we identify the change, either on a 1, 2, 3, 5-year cycle. We evaluate that change, so we go through those examination reports to see what our engineering or geological view is of what's going on. We consider what further work needs to be done, and we will undertake an assessment if we feel the site warrants it, in which we do a calculation to determine the stability of the slope. We'll then consider what temporary mitigations can be put in place. That may be a barrier, a temporary barrier that's put in place. On the other hand, it may be a monitoring regime, and that could be a temporary monitoring regime or a permanent monitoring regime, one which continues for a long period of time. We prioritize our sites and we populate the interventions in our work bank, and we deliver those, usually planned in the 5-year cycles associated with the control periods. Under the current policy, those are divided into maintenance activities, refurbishments and renewals. And there is an order of 10 change in cost with each of those. Maintenance could be something subtle like just cleaning out some drainage or making a minor repair. Renewal could be wholesale renewal of an embankment or regrading of a cutting slope. So that's the process. But you've got to bear in mind that we're applying this to 190,000 assets. An asset in our terminology is a 100-meter section of an earthwork greater than 3 meters in height. Whether that's a cutting or a soil cutting or an embankment or a rock cutting. And actually, in general level, the hierarchy of risk increases as we go down that list. Clearly, as we saw from the image of the Falls of Crooken, a boulder beneath a train can have extremely serious consequences, and it happens virtually instantaneously. In the current asset policy, what we do is we take the hazard assessed of the earthwork, so all the features seen which suggest how stable or unstable that earthwork is and how likely it is to fail, and we assign that hazard category A to E. On the left-hand side of this, we see the criticality band, which considers the consequences should a failure occur, which means that if you're in box A, it might be a single track freight line which carries 1 train a week at 20 miles an hour. If you're in box 5E on the top right-hand corner, that could be 4-track electrified railway at 125 miles an hour with a train every minute. So you can see that we're able to establish a hierarchy of risk using the structures and management techniques we have to assign the appropriate mitigation measure and the appropriate investment to maintain the quality of the earthworks. Most asset management organizations and structures will have a pretty good idea of how their assets are going to behave. If it's a widget you're manufacturing, a mechanical device, for example, the timing belt in your car, you know you need to get that replaced every 60,000 miles because someone has delivered this curve and decided that the majority of these cam belts will fail in the location between P and F on the curve. So if you do interactive maintenance, it's an awful lot cheaper to replace your timing belt than it is to replace your engine. What this means for us is that we really need to identify where those points are for our earthworks. That would allow us to initiate timely maintenance, but how do you apply that to 190,000 earthworks, particularly when you consider the images shown at the beginning of how these things were built in the first place, some of them almost 200 years ago. And that is a big challenge for us. But you can see there are huge benefits if you catch the failure early. So we also have to consider other safety, other impacts as well, not just safety, but also the impact on performance of the assets and the work on the assets and movement of them. Financial considerations, we only have a limited budget to spend, and also customer satisfaction and our reputation, which, as you'll be well aware, is not always the best. So, in an ideal world, we would predict failures before they happened. And if we were able to do that, we'd be able to run trains perfectly satisfactorily without any concern over earthwork failure, even in the most extreme of conditions. What we need to do is identify that pathway. If we can't do that, we really need to aim to robustly prevent that top event from happening. And if that's not achievable, then we at least need to have good information about the likely conditions for failure, the weather conditions that could cause it to happen, surface water runoff from catchments, that kind of thing. The water levels in the slope, which have a huge impact on the stability of earthworks. And also a measure of how stable the slope is as we see it at the moment. And our focuses have been on developing these systems and processes to give us better knowledge of our assets, and also developing methodologies where we can improve the mitigations we put in place to get an idea of slope movements, the pace of the movements, and also systems in which, if movements happen, we get a warning and we can stop trains before they reach them. So an awful lot of work is being done. We've already started it. Even prior to Lord Robert Mayor, if you look at our technical strategy document and the policy document, all of these things were R&D, R&D projects for CP6 touched on this, and we're intending to continue those into CP7. But Carmont and the Lord Robert Mayor report was a real impetus, a real change marker for us in the earthworks management business. So we monitor earthworks, we put in geotechnical instrument arrays such as inclinometers and piezometers, inclinometers measuring slope movements in the ground, piezometers measuring water levels and changes in water pressure. We also are rolling out more and more failure detection equipment. If you look on the image on the right-hand side, those yellow posts each have an accelerometer measuring movement in 3 dimensions and will allow movements to be tracked and indeed can be linked in to signal boxes, although let's not go there for the time being. We also have systems such as LiDAR. I'll just share this, this animation for you. Keep an eye on the center of the picture as you'll see what the LiDAR was picking up. Keep an eye on the blue dots. So in a period of an hour on this particular slope on the Severn Estuary, a landslide occurred and it was picked up by the LiDAR system and alerted the asset engineers to the fact that a failure had occurred. There were mitigations in place, but this kind of technology has real potential if you have a real concern about a specific location and want to be alerted as soon as anything happens there. In a lot of cases, these assets may be incredibly expensive to fix, and there's another one immediately next to it just waiting to fail as well. In 2014, the company did a full LiDAR survey of the network, and this, it's fair to say, I think has been a real game changer for us. We have point cloud data for all of our assets, so we can form a 3-dimensional model of our assets. And this has been essential for the geotechnical engineers and other engineering disciplines in order to identify features on the ground, and is a first port of call if ever there's an incident on the railway, because we can go and see what is going on the ground. We can use LiDAR to track change in height and elevation. The color shading shows the difference in height of the ground between one flight and another, and therefore gives an indication of the movements that have occurred. And we've also used the LiDAR data to consider risks and hazards from third-party slopes. Perhaps one of the most exciting uses of this information has been in modelling all of our earthworks using the Geotechnical Stability Resilience Appraisal tool, bit of a mouthful, in which we plotted cross-sections for all of the earthwork, the soil assets, soil cuttings and soil embankments, and undertaken a series of calculations, making assumptions about parameters based on geological mapping, grouping those geological strata into groups of 11 groups of material types, and then undertaking a complex range of stability calculations to work out how many of our assets are theoretically beyond their point of stability. And this is a huge, powerful tool in that assessment process in enabling us to get early warning of which earthworks are going to fail. There's also a lot of opportunities in fibre optics, whether in strain measurement or vibration measurement. I'll say a little bit more about that in a moment. And also, of course, satellite observations. And if we look at the bottom graph there, over a period of time between two passes of satellite, they were able to record movement in the embankment at Hook, which actually subsequently failed in January this year, following a period of extremely wet weather. So these technologies have promise, but they're not the fully formed article yet. So if we look ahead, the key is managing our data better. Gaia is our asset insights application, gives us an opportunity to pull together a whole load of data sets from a wide variety of locations within the business, whether that's track information, weather information, survey data, and so on, pull it to one point. We're working on that. That is in development. We already have business planning through that process, but we have high hopes for it over the coming years to ensure that we're able to provide a one-stop shop for geotechnical information. At GSRA needs more work, and that's being worked on at the moment. So just a couple of final things to talk about there. We've done some work to look at the geological cohorting, and this table of 11 material types represents a distillation of over 2,400 individual geologies found on the network. So that gives us an opportunity to say, if you've got this type of material, you can use these curves, and the potential for failure is this at these locations. It's a really powerful tool and helps the asset manager really start to get to grips with the condition of his overall asset base. And if an asset engineer has 30, 40,000 earthworks to manage, clearly he needs that help. We've also looked at a very specific distillation of all of the measures we use and methods used to classify earthworks failures, and adapted those and distilled them down to one core means of identifying earthwork failure types, which is quite specific to the railway, which allows for the fact that a lot of our natural slopes, cutting slopes, are less than 200 years old. Not like the hillsides that we see, which may carry glacial features. And so we need a specific tool to use for the railway. And there's an awful lot more to be done with earth observation technology as well, including moisture content recognition, which would be a great help in helping us understand the stability of our earthworks. Final few words. Linear monitoring technologies. We have fibre optic cable running along a lot of our network. How great would it be, wouldn't it, if we could use that to measure movements, strains, get advance notice of changes in the earthworks. We've also got the Prime tool, which looks at resistivity of the ground, tracks desiccation shrinkage, a big problem in the southern part of the country, where dry earthworks cause train delays and speed restrictions to be imposed. And, of course, climate tools, which enable us to identify weather advancing towards locations. Strangely, a dry day in Scotland, I'm sorry, I couldn't get a picture which involved lots of red and orange, but it's not that hard. So how do we manage these days when it's like this? A whole host of things I've just been through, but I think the most important thing for us is that we work cooperatively with the other disciplines, because no earthwork is isolated from everything else, whether it's the track or the drainage or indeed other assets as well. So it's really important for us. And whilst we're pushing ahead with these technologies and really making the best we can of that change driven by man, that we get to the point where we have assets that are fit for all other asset groups as well. That's it.